Look at your phone and pick it up. It feels like a simple, conscious choice. You decided to reach out, your brain sent the signal, and your hand moved. In the 1980s, neuroscientist Benjamin Libet decided to time this process. He used EEG sensors to track the exact millisecond electrical activity began in the brain compared to when the person felt the urge to move. The results were unsettling. The EEG showed that the unconscious parts of the brain initiated the movement about half a second before the person was even aware they had made a choice. In some later studies, this gap stretched to 5 full seconds. This suggests our actions might be part of a rigid chain of cause and effect. Like a domino falling, a biological trigger leads to an unconscious process, which eventually presents itself to our consciousness as a finished decision. If the decision is already made before we know it, it implies we aren't the pilots of our lives. We're just passengers reading a script our biology wrote for us in advance. In this classical view of neuroscience, free will is difficult to find. But this assumes the brain operates like a simple, predictable machine. To see if that's true, we have to look at the brain on a much smaller scale. Physicist Sir Roger Penrose wasn't convinced by the brain as a computer model. He argued that the human mind performs tasks like understanding complex mathematics or experiencing creative intuition that a set of rigid, pre-programmed algorithms simply cannot do. He proposed that for the brain to be more than a biological machine, it must interact with the fundamental randomness found in the universe, specifically the laws of quantum mechanics. Penrose found a biological partner in anesthesiologist Stuart Hameroff, who believed he'd found the exact place in the cell where this domino effect might break down. Inside our neurons are microtubules, tiny tubes acting like cellular scaffolding. They're constantly forming and breaking apart in patterns that appear almost entirely random. Hameroff noticed that inert gases like xenon can cause unconsciousness just by physically bumping into these microtubules. Because xenon doesn't react chemically, it suggests consciousness is tied to the physical structure of these tubes rather than just chemical signals. If consciousness is toggled by physical interactions at the scale, it points to a subatomic mechanism that classical biology hasn't fully accounted for. To find it, we have to zoom all the way down into the individual molecules of tryptophan tucked inside those microtubules. In 2024, researchers published a paper showing that these molecules exhibit super-radiance. This isn't a chemical reaction. It's a specific behavior of light and energy that only occurs under certain conditions. Super-radiance is a signature of quantum entanglement. Particles sync perfectly, behaving as a unified system. This breaks the rigid domino chain. In quantum mechanics, particles operate on uncaused randomness. Their output is fundamentally unpredictable. If our neural architecture is influenced by this quantum behavior, then the brain isn't just a biological computer running a fixed program. This means there is a glitch of unpredictability at the very base of our biology. The brain's decisions aren't entirely settled in advance by the laws of cause and effect. So, does this quantum randomness mean we actually have free will? It's more helpful to think of the mind as a hybrid system. Libet's experiments showed that our unconscious biology does get a head start. It generates impulses, cravings, and habits before we are aware of them. But because the system is rooted in quantum unpredictability, those impulses aren't an absolute destiny. Randomness alone isn't will, but it breaks the machine-like certainty of our biology, creating a space where the conscious mind can intervene. This intervention is powered by neuroplasticity. When we consciously choose a different path, we are physically rewiring the very unconscious circuits that Libet measured. We are training our autopilot to behave differently in the future. We are not just helpless observers. By understanding how our brains use both biological reflexes and quantum uncertainty, we can see that we have a constant opportunity to influence our own development. We use our focus today to shape the reflexes of tomorrow.